Hello and welcome in. This week's video, we're going to get into proof by induction, and this is going to be the first video in a series of videos where we go through all the major types of proof by induction that you'll have to know for IB mathematics. We're going to start this week with infinite series, and then the following weeks we'll get into divisibility, inequalities, calculus, complex numbers. You can basically do proof by induction for all of most of the topics in IB, but we're going to try to focus on the 4 or 5 that you have to absolutely know, and then the other ones you can kind of figure out during a test, and so on. As always, before we get started, there's a couple things to mention. First off, we have the Notability and the notes in PDF format down below in the description. Second, we're only going to go through 2 problems in this video to keep the video short, under 60 minutes if possible. So this will get you started, but you're going to have to do a lot more practice, probably 5 questions. If you want to get a good grasp of things, maybe up to 7 questions or 10 questions if you're trying to really master the content. And then lastly, we're going to go at a pretty comfortable speed. So if you want to go faster, of course, hit the 2 times speed button. Getting real cold, so bear with me as we go through this video. We're going to start off by talking about a sequence of numbers that is hopefully pretty familiar. And the sequence of numbers is the odd numbers starting at 1. And we get 1, 3, and 5, 7, 9, and so on. And this is going to continue up again to 2n minus 1. So if you're familiar with this notation, 2n minus 1, basically we're saying n is a number in the set z. So all the positive integers, or you could say the natural numbers. And so if we plug in any value of n in the set, it'll always guarantee we get an odd number. And if you're curious about that, pause the video and try to plug in different values of n, and you'll kind of see that this is true. One of the things that we might notice when we're looking at this sequence of numbers, maybe we're just playing around with it, is that as we sum odd numbers, something kind of interesting happens. So if we were to take like the first number, for instance, and then the first 2 numbers, and then the first 3 numbers, like that, we kind of start to see this pattern emerge. And so we start to build maybe a hypothesis, or maybe at the very least some curiosity that this type of pattern could hold as we keep adding more and more numbers in this sequence. If you remember, the sum of, well, first we should label this. This is a sequence. And if we add the terms of a sequence together, we call that a series. So we could say 1 plus 3 plus 5, and so on. Again, up to our last term, which is going to be 2n plus 1. This here, we could say, in sigma notation as well, we could say, well, there's some number I that starts at 1, and it's going up to n, whatever we decide n to be. And our formula is 2i plus 1. And what we can say is that the sum of all those terms, it kind of looks like it could be related to perfect squares somehow. Let's go ahead and try to write this down a little bit more formally. So we're going to start with our very first number. We're going to say, well, when n is 1, we plug n in here. 2, oh, I made a mistake. That should be a negative. So when n is equal to 1, our, you could say, first case is that we're just looking at the first number. So we say the sum of the first number is just 1. and the sum of 1 is 1, like that. So simple, it's kind of silly. And then we take our next one. We'll say n equals 2. And that's going to be the sum of the first two numbers. So we say 1 plus 3. And let's move all of this over to the right a little bit. Say 1 plus 3 is equal to 4. And let's do the next one, maybe in green. This is our third case. We'll say n equals 3. The sum of the first three terms. So we get 1 plus 3 plus 5 is equal to 9. And maybe one more. We'll say, let's do blue. N equals 4, the first four terms again, is that 1 plus 3 plus 5 plus 7 is equal to 16, like that. So again, we're trying to keep our example pretty simple. And what we can kind of say is that over here, these look like perfect squares. So we're kind of thinking that maybe the pattern that's starting to emerge is that we take the number, whatever it is here, in this case 1, and we square that number, and that gives us the sum of all the terms. So for instance, that would be 2 squared here. This one here would be 3 squared. 3 squared. And then down here, we have 4 squared, like that. So again, we're just taking a look at a sequence that we think is kind of familiar, all the odd numbers. We're talking about summing them all together. And as we start to do that, we notice there's kind of a special relationship. And so this lets us, again, form like a hypothesis or a conjecture. And the conjecture then is that this series is summing to n squared. So we can say here, this is n squared. And this here as well, just the expanded version, is also going to be equal to n squared. Kind of looks like it's n squared. And so this brings us to like a hypothesis or maybe a conjecture. We can say that we have this statement that we think might be true, and we want to try and prove whether it's true or not. So what can we say? We can say, well, our conjecture is that the sum of odd numbers, let's try that again. Sum of odd numbers up to 2n minus 1 is equal to n squared. So we can say something like that. And we should probably say that conjecture, there's a formal definition for it, and a conjecture is a statement that we think is true, but we need to prove whether it's true or not. So it's kind of like a hypothesis. We're saying, oh, there's this thing that we want to investigate and prove whether it's true or false. And we can do that using our various methods of proof. So that's things like direct proof, proof by contradiction, and then of course in this video we're talking about proof by induction. For conjecture is a statement that is believed to be true, but has not yet been proven true. Oh, let's move this out of the way so we can see everything on the screen. So that brings us into our actual method of proof by induction, and we're going to take a look at these 3 major steps. So let's take our statement and we'll put it up as our thing to prove. So we're going to say, using mathematical induction, prove that this statement is true. Again, our statement is what we set up above. We want to show that the sum of odd numbers is equal to n squared. So the very first thing we need to do is move into our first step. And we'll try to make this a certain color so it stands out. Our first step is called the base case, or the initial case. So let's do it like this, the base case, or the starting case. And the starting case is written as p of 1, like that. And we'll talk about this notation at the end of all of this. So for now, we'll just say p of 1 is representing the case where n is 1, our base case. And sometimes p of 1 can also be written as p sub 1, like that. And this is proving that this works for at least one case. And that kind of makes sense. If it's not true for even a single case, then we can kind of expect that it can't be true for all cases. And so we're going to start here with this base case. Our P, I guess we can also mention, stands for proposition. P stands for proposition. Again, we'll get into notation a little bit later on. Right now, proposition. We're just trying to focus on the idea and how to do it. We say for our base case, and let's change the color of that actually. What we can state is that our base case, again, is n equals 1. So this up here is our statement that we're trying to prove. We call this p of n. And so in the case where n is equal to 1, we say p of 1. And this is the case that we talked about up here. So we've kind of already proven this. We'll just copy that result from above. When n is 1, we're taking the sum of the first term, and it should be equal to 1 squared. And so it's so simple, it almost is kind of hard to see what's even happening, but we can say that this is true. The sum of the first term, 1, is 1, which is also equal to 1 squared. So we've proven that for this conjecture, again, the sum of odd numbers is equal to n squared is true for the very first case, the base case. The base case is always going to be the easiest step of this process. It's basically guaranteed points on a test, so make sure you always write down the base case. Plug in your starting number. One thing we should say is that our starting case is not always 1. For mathematical induction, we're working with the natural numbers, which is the set n, or it's going to be the positive integers, so z plus. We'll see that happen over and over again through all the problems that we work in this video and the videos to come. Maybe just to, again, make this a little bit clearer, we can even say that instead of proving the first case, we could also do the second case. So what we could say is our second case here, again, also shown to be true. Our third and fourth case, we also proved. As we're working through a question, of course, you only need to pick one case. We're just showing 2 here because sometimes it's a little easier to see what's happening when we're summing 2 terms versus summing just a single term. All right, that is our base case. That brings us down to the second step of proof by induction. This is known as the kth case, sometimes known as the general case. So we'll say general case. This is the inductive hypothesis. These names are not important. You do not have to label these steps as such, but it can kind of help sometimes to write them out like this. And so this is the P of k, sometimes written as P sub k, like that. So in this step, what we're saying is that we're trying to write a statement that shows that this is true for any number k. So what you can kind of think here is k represents any number. And so we could say, for instance, that this could be 10. It could be 100,523. It could be 76, for instance. So k is representing all of these numbers basically. And just like before, we're taking 1 and plugging it in for n. Here we're saying, well, n is k. What would it look like if we're looking at the kth case? Well, we're saying, well, starting with 1, again, adding all the odd numbers, in this case up to the 2k minus 1, should be equal to k squared. So again, we could say k is, let's say, for instance, that k is 10. In that case, we'd be looking at 1 plus 3 plus 5 plus 7 plus 9, all the way up to 19. So we're saying that the sum of these numbers here is equal to 10 squared, like that. So all the odd numbers up to 19 added together should be equal to 100. Now, you're probably thinking, well, how can we write this down like this? Isn't that what we're trying to prove? Isn't that just the formula with k inserted? And that is absolutely correct. So what we're saying here is that this is a hypothesis. Again, we said this is the inductive hypothesis step. So this is a hypothesis. Or you can say that this is an assumption. And let's go ahead and highlight that because we're going to come back to it. This right here is our assumption. We're saying, well, let's trust the process. For the kth case, we're going to say, let's assume this to be true. Now, why would we want to assume something to be true that we're actually trying to prove? If we go back up here to this initial set of numbers, one thing we might notice is that as we went through each of these cases, we kind of saw that these results kind of built on each other. So, for instance, in the third case, we had 1 plus 3 plus 5, and we summed that up, and it equaled to 9. And down here, in the fourth case, we can kind of reuse that result. We know this is 9, and over here, we just added 7 to both sides. So it's kind of like if we know the case here, the case after, the consecutive case, also kind of gets proven at the same time. And so try to keep that intuition in mind as we move down through here. So we're looking at the general case again. We're not doing too much here. This is actually a really easy step as well. We're just taking k and plugging it into the formula and saying we're assuming this to be true. Why would we want to do that? Well, let's go ahead and take a look at the final case and see the magic that kind of happens when we connect our k case and the case after together. Our next case is the consecutive case. And let's do this one in red. So this is the consecutive case. And officially, it's known as the inductive step. This is actually when the induction is complete and the proof comes to its conclusion. So if this will behave, there we go. This is the inductive step. And this is known as P of k plus 1. So again, if we look at the previous case, which was 10, the consecutive case would be the 11th case. And we'll write that out here in a second. Once again, you might see this also written as P of, or P sub k plus 1. So here we get P sub k plus 1, like that. Let's move that up. In the consecutive case, this is also going to seem probably a little bit silly. And what we're going to say is, well, we're plugging in n equals k plus 1. So again, we're going to take our formula. We're going to say 1 plus 3 plus 5, sum of all the odd numbers, up to 2k minus 1. That's our, from before, our k case. And now we have this new one, 2 of k plus 1 minus 1, like that. And that should be equal to, according to the formula, k plus 1 all squared, like that. Again, to keep things concrete, we'll show what that looks like for a concrete number. So we're going to say if we have the 11th case, so we're just going to change that to 11. Then this whole series is now going to go up to 21. And we're going to get plus 21 is then equal to 11 squared, which is 121. So we have some case, then we're trying to prove the case after it as well. Now, like we mentioned, there's a lot of overlap between the k case and the k plus 1 case. So again, here we can say that this whole part up to 19 is the same. Oh, that's not a good color. Let's try yellow. This whole case, oh goodness. So this whole case up to 19 is exactly the same, and then we can prove the case after by adding the same thing to both sides and showing that that one's also true. Now again, you might be thinking, this is silly. Why are we taking our formula and plugging into it as if it's true when we know that it's not? And again, you're absolutely correct. So what we can say here is that this is what we're trying to show is true. So what we usually say is that this is our goal step. It's where we're trying to get to. And let's put some blue on that. Oh, there we go. So this is our goal. And when we say it's our goal, we're saying that we're trying to show that whenever the assumption case is true, that the inductive step, the case after it, is also true. So this brings us to the most important part of proof by induction. We're trying to show that for every case, that the consecutive case is also proven true. And again, we'll talk about why we need that to be true here in a second, but that's what we're going to try to do. We're going to try to go from our assumption step here in green to our goal here in blue. Okay, we got the color set. So the final part of proof by induction is we need to go from our assumption to our goal. We need to show that for any case, the case after it also is proven true. If we can prove them together, it will prove it true for all numbers, as we'll see here in a second. So when we're actually working this in a problem, what we're going to do is we're going to take our goal that we see here, and we're going to put it at the bottom of the page, because that's what we're working towards. So we want to stay really organized as we're going through this process. So we're going to take our goal. Let's see if we can grab that. We're going to move from our assumption down to our goal, again showing that when the assumption is true, the consecutive case is also true. And we do this using algebra. So kind of our first step in this process is to notice, well, let's put that below, is to notice similarities between the assumption and the goal. What we can say is that if we look closely, one similarity, like we mentioned above, is that a big part of this, actually this whole left-hand side, is exactly the same up to here. In fact, in our consecutive step, all we did is add one term to both sides. So what we do is to take our assumption step, starting with that, and we want to add the same thing to both sides. So again, we have a true statement here. It's assumed to be true. Using algebra, we can add a similar term to both sides. And we add this new term on the left-hand side and the right-hand side. So we're going to add a 2k plus 1 minus 1 here. And we're also going to add that on the right-hand side. So we're going to have k squared over here. And then this new term, 2k plus 1 minus 1. If you're asking, how do you know that we can do that? Well, following the rules of algebra, as long as we have the same thing, excuse me, as long as we have the same thing to both sides, then our equation is still true, correct? So over here, we notice, well, wow, this is now, again, the left-hand side of the goal. If this right-hand side turns into k plus 1 squared, we've then proven, again, that the assumption and goal are proven together. So this is pretty quick on our right-hand side. So what we can say over here on the right-hand side is that we have k squared, we have 2k plus 2 minus 1. And if we rewrite that one more time, we get k squared plus 2k plus 1. And if we factor that quadratic, it does indeed give us k plus 1 squared. And so this completes our proof by induction. Now that's a lot to process. We have a lot to talk about here. So let's try to do a quick recap. If we go up to the top, we started with our very first case, called our base case. And we proved that this proposition is true for the very first case, or this statement, sorry, is true for the very first case. So again, we know if it's not even true for the first case, it can't possibly be true for all numbers. After we proved it true for at least one case, we then came to our general case, and we said, well, for any number, let's assume this to be true, which seems kind of silly. But then we go to the case right after, and what we showed is that whenever our assumption is true, the case after it is also true. And so what this does is it kind of gives us this case of dominoes, where maybe this is our very first domino here. This is our first domino here. And we can call this the n equals 1 domino. So this is our first domino. And then over here someplace, we have our second domino. And this domino is some domino in this long line. And we're going to say it's the k case. Again, this could be 69. This could be 71. Could be any number, 1001, for instance. So this is one of the dominoes. And we said, well, let's assume this to be true. Can we see if there's anything true about the domino right after it? Okay, so domino has no E. So we then have the domino right after. What we're saying is that every time we have this domino, the domino after it falls as well. So for instance, if we start with the first domino, it's going to cause our second domino to fall. The second will cause the third to fall, the third to the fourth, and this will continue on to infinity. So it's a really clever use of logic in mathematics to show that if we can prove the first case, and then we can prove two consecutive cases together, then this domino effect happens, proving all the cases up to infinity, and basically for all the natural numbers n, or for all the positive integers. And so, again, it's a little bit of a stretch for our brain, but if you go back to where we started up here, and you take a look at these two cases, the third and the fourth case, you can kind of see that for every case, the case after is kind of also true because we're just adding the same thing to both sides. And so any place where that's true, this proof by induction method is going to be really helpful to help us solve problems. The final part of this question is to give our statement. And our statement looks like this. This is a summary of everything we just talked about. So we say our base case is true. We say our k plus 1 case is true whenever our k case is true. So our consecutive case is always true when our assumption step is true. Therefore, by mathematical induction, this is true for all of the numbers starting at the base case, which is 1, up to infinity. Now, we mentioned at the very beginning that we would talk about this P of n notation. So P of n is a propositional function for instance, P of n is the statement the sum of all numbers, sum of all odds, or we could say odd numbers, to 2n minus 1 is equal to n squared. So it's a statement, generally for n. As soon as we plug a number into this function, for instance 1, the statement is now the sum of all odd numbers to 2, n is now 1, is equal to 1 squared. So 2 times 1 is 1, minus 1 is 1. So the sum of all numbers up to 1 is equal to 1 squared. So we can plug numbers into like this statement, and it gives us different cases of this statement. So when you see this P of n notation, you can honestly just ignore it if you want to, but if you're curious about what it means, it's basically a way for us to mathematically take a statement and describe it in terms of different cases, which we've seen above. So the first case is going to be P of 1. The general case will be P of k, and the k plus 1 case is P of k plus 1. Okay, let's jump down into our practice question to wrap things up. Okay, so before we get into the practice problem, there's one more thing to mention, and that is, how do we know whether we should use proof by induction or not? The simple answer is that for IB, the question will tell you. So it's really easy. On a test or on homeworks, there will always be the statement, prove this conjecture, prove this statement using mathematical induction. But in terms of real life, you don't know. So this statement that we are trying to prove, again, is the sum of all numbers the sum of all numbers is equal to n squared. Now, as we talked before, we have lots of different methods. We have proof by contradiction, we have direct proof, and we also have like visual and geometric proofs, are just some of the ones that we've probably seen throughout high school at least. If we take a look at this particular question that we just solved as an example, what you might notice is that this sequence, or actually this series, so 1 plus 3 plus 5 plus 7, again, up to 2k minus 1, you might notice that this is a certain type of sequence. Maybe you noticed this from the very beginning. What we can say is that this is an arithmetic sequence. And specifically, we can say that the common difference is 2, and our first term is 1. And we have methods to find the sum of an arithmetic sequence. So if you have a little bit of extra time, go ahead and see if you can prove that this statement is true directly. So use direct proof. To show that this statement is true. And what that helps us kind of realize is that proof by induction is not going to be the only way to prove a conjecture or a statement. In real life, you're going to look at the options that you have available to you and try to decide if proof by induction would work or not. Again, for IB math, they'll tell you. You can just not worry about it. But generally, if you're working with numbers that are part of the set all natural numbers or part of the positive integers z plus, proof by induction is going to be pretty helpful. Okay, let's jump down to the practice problem for real this time. This brings us to practice problem number 1. Practice problem number 1 is asking us to prove that this statement is true for all n in the set z plus, so all positive integers or all the natural numbers. We have it here in sigma notation, which is maybe not the easiest to read. So let's go ahead and take the sigma notation and we'll expand it out. We say I is 1 to start out, so we put 1 in here, we get 1 squared. When I is 2, we get 2 squared. And again, we add all the terms together, 3 squared. So what we see here is that we're doing the sum of squares, or the sum of all the squares, and we're saying that as we add all of these squares up, pin troubles, okay, so we're saying that the sum of all the squares up to the nth square, and it's dead again, up to the nth square is equal to this formula, n plus 1, 2n plus 1, all over 6, like that. So that's it in expanded form. Like we talked about before, we start with our base case, and let's pull that in. So we have our base case. We say our base case in this one, again, it starts at 1, so it's going to be p of 1, or p sub 1. We say n is equal to 1. If we plug it into the formula, we say, well, the very first term is 1 squared, so we're just summing the first term, and that should be equal to this formula over here, where n is 1. So we get 1, 1 plus 1, 2 times 1 plus 1, and all that over 6. So if we simplify down, we get 1 squared is 1, and in the top we get 1 times 2 times 3 is 6. We get 6 over 6. So 1 is equal to 1. And so just like that, we have the proof for our base case. As always, this one's going to be really quick and simple. All right, let's move to our general case. Go ahead and pull that in. Our general case is, again, when n is equal to k. So we say n is equal to k. This is our assumption step. So we're just plugging it in. We're saying 1 squared plus 2 squared. All the squares up to n squared, which we're now saying is the kth number. So k squared is equal to this formula here. And so in this case, our n is k. So we get k. We get k plus 1. And then we get 2k plus 1. And let's move that by the way. And all of that is over 6. So again, we're going to label this as our assumption. So this is our assumption step. Very quick and easy. We're just replacing our n with k, and we're assuming this to be true. And then we bring in our consecutive case, or our k plus 1 case. Our consecutive case is to do this exactly again, except in this case we now have the k plus 1 term. So we're just going to take our left-hand side and add in one more term. So k plus 1 squared. And then over here on our right-hand side, we have to again take k plus 1 and plug it into our original formula. Every time there's an n, we're going to plug in k plus 1. So we get k plus 1, then we get k plus 1 plus 1, and then here we get 2, in parentheses, k plus 1, plus 1, and then all of that over 6. And we say again that this is our goal. All right, so that's our goal. So like we saw before, we're going to take our goal, put it in a place that we can see it as we work through the steps. And we're going to put our assumption at the top of our page. So let's copy both of those. Okay, so we have our assumption step at the top. We have our goal in the bottom right, which we're going to have to move kind of as we work through this problem. And our first step, as we saw before, is to notice any similarities. So we want to note similarities. We're going to pray that our pen lasts for the rest of this video. And once again, we'll put our similarities in pink. So we can say that our similarities for these two is going to be all the terms up to k squared. And so down here, our similarities go all the way up to this part right there. And so what we say is, well, the different part is this k plus 1 squared. So if we can take our assumption step and we can add a k plus 1 squared to both sides, we can start working towards our goal. So to do that, we'll rewrite this left-hand side, say 1 squared plus 2 squared plus 3 squared plus 4 squared. Again, all the way up to k squared. And this is the part where we add our new term. We say plus k plus 1 squared. And then on our right-hand side, this part will stay the same. We have k times k plus 1 times 2k, if our pen will work, 2k plus 1 all over 6. And again, we're adding a k plus 1 squared to this side as well. So we get something like that. So if we can take, again, our right-hand side and show that it's equal to this expression down here, our goal, we are finished. Like we saw before, this is all algebra. So we're trying to take our right-hand side, manipulate it using algebra to get down to our goal. One thing that we might be tempted to do is to take our first term here, to take this one, and distribute it out and multiply things out. If you have a bit of free time, I suggest that you try doing it this way. So take the k, multiply it by the k plus 1 and the 2k plus 1, and try to combine things together. What you'll kind of notice is that things get very messy very quickly. It's not impossible, but it's going to give you a cubic, and working with cubics is quite cumbersome. And so you just have to kind of see this question at least one time previously to know that there's a long way and a short way. And so we're going to do the short way here. We say instead of multiplying this out, we're going to try to get a common denominator between this term and that term. We take our right-hand side and we try to get a common denominator. To get a common denominator, we take our second term and we multiply the top and bottom by 6. So what we see here is that this one is going to become 6 times k plus 1 over 6. Those two fractions will combine together. And let's take our goal again and move it down. So we get k plus 1, 2k plus 1, then we get 6k plus 1 squared all over 6. Again, we do something here kind of interesting. If you're working this problem on your own, try to think about it and work it through. This requires a very specific algebra step that you just kind of have to see at least once. which in my opinion is kind of silly, but as much as a math class will curate problems to make them easily solvable, these types of proof by induction do have a couple of weird algebra steps that you just have to be familiar with. So here again, you might be tempted to distribute and multiply things out, but instead, we actually want to take a k plus 1 from the first two terms. By that, what we want to do is we want to notice that there's a k plus 1 here and a k plus 1 there. And so again, a bit counterintuitive, but what we're saying is we're going to take a k plus 1 out front, going to factor it out, and that's going to leave us with k times 2k plus 1, and then plus 6 times k plus 1. And again, our denominator is 6, like that. What we see here is that if we compare ourselves to our goal, we have a k plus 1, so we're getting closer. If we can take the inside of the square brackets and change them into those other two factors, we'll be all done. So moving down, and once again, getting our goal out of the way. Excuse me. What we can say here is that this is k plus 1. Inside of our brackets, we are going to multiply it out this time, and we're going to get 2k squared plus k, and then we're going to get plus 6k plus 6. All of that, again, is going to be over 6. Bring us down to our next step. We say k plus 1 is now multiplied by this quadratic, 2k squared plus 7k plus 6. All of that being over 6. Again, we know that for all the problems we solve in IB math, the results are always true. And so we can kind of take a shortcut and say, well, this quadratic probably factors and turns into these last two terms in our goal. But just to be thorough, we'll go through the process of doing that. So up here we have 2k squared plus 7k plus 6. To factor this, we're going to use AC split the b. See the short video on how to do that. So AC split the b. We're going to take our a, which is 2, our c, which is 6. We're going to multiply together, we get 12. We want the factors of 12 that add up to 7, and so we say 3 and 4. We take our b, which is 7k, and we split it into 4k and 3k. You'll have to do practice to know which one to put first. And then plus 6. We then factor by groupings. We take those first two and these last two. We factor out 2k from the first two, and so we get k plus 2. And then we factor out a 3, and we get k plus 2. And so that turns into 2k plus 3 for our first binomial, and our second binomial is k plus 2. And so we pull that result over here, and move down a little bit, move our goal down a little bit again. And we can finally say here that this right-hand side is now k plus 1 times k plus 2 times 2k plus 3 all over 6. And if we really want to, we can do one final step, and we can say this is k plus 1 k plus 1 plus 1 times 2k plus 1 all over 6. And then keep in mind, again, that all of this work is to show that it's equal to our left-hand side, which is this right here. Ooh, goodness. So we get that. We pull that in, and we say that is our goal. That's what we were trying to get to. So we've now proven that whenever our assumption case is true, if we modify it using the rules of algebra, it gives us our consecutive case to also be true. And so by mathematical induction, our base case is true, and our k plus 1 case is true whenever our k case is true. And so just like before, we can pull in that statement and we summarize all this work. We say our base case is true. Our inductive step is true whenever our inductive hypothesis step is true. Therefore, by mathematical induction, this is true for all n from 1 or greater within the set Z. And in this case, we could say here that this is Z plus. Okay, that brings us to the end of the practice question and also the end of this whole lesson. Let's do a quick recap as always. So if we get up to the very top, we start off with a very simple sequence, odd numbers, and we notice that as we sum odd numbers together, there's this pattern that emerges that it's actually equal to the number of terms squared. So we summarize this in a statement, and we call this our conjecture, and we set off to prove this conjecture using this new method of proof called proof by induction. For proof by induction, there's always 3 steps. We start with our base case, and we have to prove that at least one case is true, and that makes sense. If there's not one case that's true, we can not do the rest of the steps. Once our base case is true, we move to our inductive hypothesis, our general case. And we say, well, let's assume that it's true for one of these cases. Can we show that the case after is also true? Can we prove them together? So it brings us down to our inductive step where we say, here's the case right after, the consecutive case. We take our assumption step, we add things to both sides using algebra, which is always true, and that brings us down to our goal, our inductive step. And so by doing that, we prove again that any general case and the case after it's always true. And so kind of by this domino effect, we can start at any number. It could be 1, it could be 63. If we show that 63 is true, then the case after it is also true. And the case after that is also true. And the case after that is also true. And it proves it for all the cases. So this is the method that we see. And so we kind of put this statement at the end. We talked about this propositional function notation, which again, you don't have to worry too much about. You can just kind of copy this statement and use it wherever you need it. But it's basically saying that this function is a proposition, and for different values of n, it gives us different propositions or different statements that we can then prove. When do we know to use induction? In IB, they'll tell you to use it, so you don't even have to worry about that. In real life, you try to use different methods depending on the type of math that you're trying to prove. And then that brought us down to our practice problem. And on our practice problem, we try to prove that the sum of all the squares up to the nth square is equal to this formula, n times n plus 1 times 2n plus 1 over 6. And so we solve that, again, using the same 3 steps, proving our base case first, which is always really quick and easy. Bring us to our general case, which is also a very quick step. You just swap your n's for k's. We're assuming this to be true. And then that brings us to our consecutive case, our inductive step, where we say, can we take our assumption and change it into this goal? Can we show that for any general case, the case after it, the consecutive case, is also true? And so we compare our goal and our assumption step, and we say, what's similar? What's different? And we say, oh, the goal step has this k plus 1 squared. So let's add that to our assumption step on both sides using algebra. And then everything after that is algebra. And it's always going to be true that the algebra steps are going to be a lot of work. Okay, so this is where we're going to do most of the work in the inductive step. And then once you get down to here, you see your goal emerge. You are complete with the proof, and you put your statement. Again, the base case is true. The consecutive case is true whenever the general case is true. Therefore, by mathematical induction, we are complete and done with this proof. Okay, if you have any comments, if you notice any mistakes that were made, please put them down in the comment section below. And until next time, I will see you in the next video.